Welcome back, everybody, and we are going to dig in now to the second half of Chapter 4. The first half was all about calculating the formula mass of stuff and learning percent composition and grams of an element and a sample and chemical formula, empirical formula, all that good stuff. And now what we're going to do is also balancing chemical equations. And now the second half of this chapter, we are going to sort of combine all that stuff that we learned about in the first half with things that we can actually do in the lab. Right? Because, like, if you looked at the chemical reactions, they all sort of go by number of atoms or number of molecules, right? Like 6 of this react with 3 of those and so on. But we can't count individual atoms or molecules. They're way too small. But what we can do is we can measure their mass with a scale. You know what I mean? Just kind of scoop some stuff on a scale and measure the mass in grams. And what we're going to learn about now is how we connect grams, which is something that we can measure pretty easily in the lab, with those chemical reactions that we were learning about, right? And we're going to use all those like gram formula masses and all that stuff together to do what we're going to do. So let's get into it. The first thing we need to know about are units of measurement. So here's some questions. How many roses are in a dozen roses? 12, right? There are 12 in a dozen. A dozen is 12. 12 is a dozen is 12. How many shoes are in 12 pairs? There are 24 shoes in 12 pairs, right? I mean, does that make sense? Because one pair is 2. 2 is equal to one pair, right? And when you go and buy paper from the, like printer paper from the store, you buy it in a ream. That's what that little package of paper is called. And there are 500 pieces of paper in a ream, right? Okay, so how many pieces are in 2.5 reams? 1,250. Very nice, right? Because it's 2 reams, that's 500 each, that's 1,000, then a half a ream, it's 250, right? So that's 1,250. What do these things all have in common, and why do we even bother with a ream or a dozen? Why? Because it's convenient, right? It packages things into amounts that are easily and conveniently manageable. Like buying eggs by a dozen is pretty good because we use them about like a dozen at a time. It's nice. We can pick it up and carry it. It lasts us about as long as we need to next time we go to the grocery store. We don't want to buy eggs one at a time. That would be silly. That would be a pain in the butt, really. And we don't want to buy them like by the 1,000 at a time because that would also be kind of inconvenient, but in the other side of buying them one at a time, you know? Same thing with like buying printer paper. We don't want to buy paper one sheet at a time because that would just be so annoying. But we also don't want like an entire pallet of like 50 million pieces of paper. Like we just need a nice unit or chunk. Does that make sense? So we have all these like units of measurement that are super duper convenient for whatever we're doing. Right? Just convenience. I mean, really, it's all about making our lives easier. All right? So here's the thing. Here's how this is going to work for chemists, right? Here's a chemical equation that we have. 2 hydrogens, right, are going to react with 1 oxygen, and it will produce 2 water molecules. Now, how many hydrogens do we need for every oxygen? Well, 2, right? We need 2 hydrogen molecules for every 1 oxygen molecule. Same thing if you don't want to do it 1 molecule at a time, because that's a pretty small amount. How many dozen hydrogens do we need? Well, how about 2 dozen, right? We could use 2 dozen hydrogens, right? So the question is, can we measure 2 dozen hydrogens? Can we measure 2 hydrogen molecules? No. These things are so unbelievably small. Like maybe somewhere in some lab, super fancy, we can isolate 1 hydrogen molecule at a time, or maybe even a dozen at a time. But for like regular, normal like chemists working in a lab, it's not too far off of what we have here. Measuring a dozen at a time is not going to be worthwhile, like at all, and it's going to be impossible to do. So we can't do this 1 or 2 molecules at a time. So chemists need to come up with some bulk unit of measurement that works a lot like these, that works a lot like the dozen and the pair and the ream, but is convenient, but is a chunk that's convenient for like a chemist. Do you understand what I'm saying? So we have done this. We have come up with our own unit of measurement, And this is a unit of measurement for really, really big numbers. And we need really big numbers because we have to measure atoms and molecules in huge quantities at a time, because these things are so unbelievably small. Like, these things are just like, it boggles the mind how small atoms and molecules actually are. And that unit of measurement that we love so much, it is the mole. I don't know, like, it could be mole short for molecules. I can't really honestly remember the reason why we call it a mole. Everyone's like, why do we call it a mole? Why do we call it a dozen? I don't know. Why do we call it a ream? A ream is a silly name for a unit of measurement. Why do we call it a pear? Why is 2 a pear? A pear is a fruit that is delicious and grows on trees. A pear is not 2. I don't know. It really doesn't matter. What matters is that a mole is a unit of measurement. It is quite literally like a version of a dozen that is used for chemists, right? But instead of 12, because we can't really measure atoms 12 at a time, it actually ends up being this number down here, 6.02 times 10 to the 23rd. How did we come up with that? Well, here's the deal. Way back in the day, like hundreds of years ago, there was this dude named Avogadro. And Avogadro saw this problem of like these chemical equations that work with numbers. He knew that atoms and molecules work together like one atom and then another one atom. But he couldn't count atoms individually because the only thing we could do in lab was grams. So the chemical equations were in numbers, but the only thing he could actually do in lab were grams. So here's what he did. Oh, and this is just something that you have to memorize. This is one of those weird things that New York State says you just have to put inside your brain. So what he said is that however many atoms it takes to have 12 grams of carbon 12, now this is the clutch part, of carbon 12, however many number that is, well, we will call that a mole. So what he did was he defined it first and knew that generations after him would be able to come up with the actual number once science had advanced further than where he was. His noggin is the one that was advanced. So what this means is carbon 12 here has 12 nucleons. It has 6 protons, 6 neutrons, right? So what he's decided is that if you, however many atoms it takes to have 12 grams of this, that number he will call a mole. And the reason why he did that is because that turns out to be the number of particles in the formula mass. So if you know the formula mass, you know how many grams you need per mole. It's a beautiful, clean, easy conversion. And it works out so well that we call this number right here, that is called Avogadro's number. And you just got to lock it in your brain. 6.02 times 10 to the 23rd. The chemist's dozen. It's the number of atoms and molecules we group together for our basic unit of measurement when we're like trying to measure out numbers and stuff, so that the reaction happens properly. So here's some questions for you guys. How many atoms in 1 mole of atoms? Well, let's go with Avogadro's number. Lovely. Oh, hey, one other point that I may have missed here is that it's really important to get the number of atoms and molecules right when we want a chemical reaction to happen. Because if you don't have the right ratio, right? If we go back up to this equation up here, right? It's like a 2 hydrogens to 1 oxygen, and if you don't have a 2 to 1 ratio, it really doesn't happen. It just can't, because you don't have the right ratio. But once you hit the right ratio, bam, then you get some action happening. But again, without the right ratio, it doesn't work. If you know about cars, it's kind of like if you're running too rich with too much fuel, the engine doesn't run very well. But if you're running too lean with not enough fuel, then it's not going to run there either. You have to have just the right ratio for these chemical reactions to happen, because you have to have 2 hydrogens for every 1 oxygen. Otherwise, it just simply can't happen. You guys picking up what I'm putting down? Delightful. All right, so the next one, this one should be pretty easy, right? How many water molecules? Oh, also this is like a thing. How many molecules? This is like numbers. We want to know numbers if they're asking how many. are in 2 moles of water. Pretty simple, right? We just take Avogadro's number and we multiply it by 2. But I want to show you this. It's kind of silly right now, but later on you'll see and be like, yeah, thanks. Remember well, no, I'm just going to do this. So we want to go from moles to numbers, so we got to get our equality first. And we know that 6.02 times 10 to the 23rd of anything, in this case molecules, is equal to 1 mole. Right? Delightful. So what we're going to do is we're going to write down what we're starting with, and in this case we're starting with 2 moles, and we're going to put that in the upper left-hand corner of our lines of pain. You dig? And the reason I'm drawing this out is because sometimes this is going to get ugly and complicated, and this is the procedure we use to make sure that all the math is being done right, because everyone's like, you just multiply it. Like, well, are you sure? This is how we're going to make sure, right? This is how we make sure that we're doing the proper math. Because if we have moles in the upper left, we need to have moles in the lower right so that those units can cancel out. And according to my equality here, I have 1 mole. So I need mole, bottom right, and 1 mole is equivalent to 6.02 times 10 to the 23 molecules. You dig? Sweet. So now I'm going to go do some math, and that'll be what? Right? I mean, you knew that you just needed to double it, right? But this is one of those things where your brain just does math without you even knowing what it's doing, and it's doing this, right? It's like it's getting this equality. It like gets the equality, and it's like lines them up right, which is easy when it's just times 2. But when things get ugly and the numbers get complicated, that's where like using these lines of pain and making sure that your units cancel out so that you're multiplying when you should and dividing when you should. It's a skill you're going to love later on. All right, next. How many molecules, right, that's definitely numbers, right? How many molecules are in 0.5 moles of that stuff? Copper sulfate. All right, so we are going from moles to numbers, and this is one of the things, man, I don't know if I can do this in my brain, so I'm going to write it out. I'm starting with 0.5 moles, and I'm going to put that in the upper left of my lines of pain. Now the equality I'm using has moles and numbers, right? So we know that it's 6.02 times 10 to the 23 number of anything is equal to 1 mole. So if I have moles in the upper left, I'm going to want moles in the bottom right. And 1 mole is equivalent to 6.02 times 10 to the 23rd. Let's make sure that's there. Double check. Moles indeed do cancel out. It'll be, okay, so it'll be, the math will be 0.5 times 6.02 times 10 to the 23rd. That'll be 3.01 times 10 to the 23rd molecule. All right, so the thing is, we can't count atoms or molecules. But if we know that 1 atomic mass unit is going to be equal to 1 gram per mole. Now, why? Remember Avogadro, he said that carbon-12, right, that 12 grams of this is going to be equal to 1 mole. That means that we can take our atomic mass units and just change it to grams per mole, because 1 mole of nucleons of carbon-12 is going to be equal to like 6.02 times 10 to the 23rd. It's a wonderful conversion thing. Here's how it works, guys. First, there's 2 things. The first one is going to be the gram atomic mass, which is like basically like the mass of like 1 mole of stuff. So the atomic mass can be expressed in grams per mole like this. Oops, hold on, let me get a pen right here. If carbon is equal to 12 atomic mass units, it is also equal to 12 grams per mole. Right? Because I mean that's how Avogadro set it up. That's how he defined the mole. Same thing with sodium. Sodium weighs approximately 23 atomic mass units, which means it is also 23 grams per mole. So if we take sodium and we scrape 23 grams of this stuff onto a scale, that means we have approximately 6.02 times 10 to the 23rd atoms of sodium. And that is the link between grams that we can measure in lab and numbers that we see in the chemical equations. That's it right there. So we can measure the mass of 1 mole of a substance so we know how many atoms we have in our like beakers and whatnot, so that we can get the proper ratio of atoms and molecules so that when we put them together, we can have the chemical reaction that we actually want because we got the ratios right. You guys get what I'm saying? Look at this conversion. This is a very good conversion. It's a very nice conversion to know. So, how much does 1 mole of calcium weigh? I don't know. Well, it says right here that the atomic mass of calcium is going to be 40.1. So it says that calcium, it's 40.1 AMU. So how much does 1 mole of calcium weigh? Well, watch. I'm going to convert atomic mass units to grams per mole. Watch carefully. Watch carefully. There, I did that. Nice. I got the conversion right. So if it's 1 mole, it's 40.1 grams. Easy, right? How about what is the weight? Okay, the weight is always going to be grams of 2 moles of silver. All right. So for this one, I might need to like break out my like. I'm going to need to use my like brain here for like mathy stuff because we're going to start with 2 moles of silver, and I'm going to put that into my lines of paint right there, and I'm going to need my equality here. So I'm going to come up to here, and silver is 107.9 grams per mole. There, I automatically did my atomic mass units to like grams per mole. So what that means is 107.9 grams equals 1 mole. 1 mole of silver equals 107.9 grams. You dig? So if I scraped 107.9 grams of silver onto my balance, I'd have 6.02 times 10 to the 23 atoms of silver. Or if I had 1 mole, I would have, if I could count them all out, I'd end up with 107.9 grams. Okay, great. So coming back over to here, we need to go from moles to grams. So this is what we need to end up with is grams. So if I have moles in the upper left, I'm going to need moles in the lower right. And according to my like equality that I have over here, how many is that? 1 mole. 1 mole is equal to 107.9 grams. Yeah? So I will end up with, check me on that math though, I'm not really sure I did that really quick in my head. But you guys get what I'm saying? Do you see how this works? So here, we just went from number of moles to number of grams, right? That's pretty sweet. That's pretty sweet. So how much does 1.3 moles of sulfur weigh? Well, guys, we're going to do the exact same thing that we did like almost every other time. First thing we're going to do, let me see how much. Okay, so I'm going to go from moles to mass, right? And it's going to be sulfur. So if I look up sulfur, sulfur is 32.1 grams per mole. And I'm starting with 1.3 moles. Put them into the upper left-hand corner of my lines of paint. And if I have moles in the upper left, I want moles in the bottom right. So I will put 1 mole is equal to 32.1. All right, 41.73 grams of sulfur. Okay, yeah, got that one right. I should do this. I should be able to do this. Okay, so now, that was called the gram atomic mass. That's for atoms. That's why we call it gram atomic mass, 1 atom at a time. Now, if you happen to have a molecule or a compound, like a bunch of like different elements all smashed together, or same elements all smashed together, it's just like we did before. It's the gram formula mass. Gram formula mass. Same thing as the atomic mass or the formula mass, but now we just put the word gram in front of it. So what is the gram formula mass of ammonium phosphate? Well, just like before, right, we're going to find out the number of nitrogens. So 3 times 1, 3 nitrogens. Each nitrogen weighs 14. We have a grand total of 42 from nitrogen. We do the same for hydrogen, for phosphorus, and for oxygen, and we add them all up. Here's the clutch. The difference between like the atomic mass or the formula mass and the gram formula mass are just the units. And all we have to do is take our atomic mass units and then erase them and write down grams per mole. That's how we get our gram formula mass. Thank you, Avogadro. That's all that conversion is. Does that make sense? So now one thing I want to write down for you guys, and this is something I need you to like commit to memory. Okay, this is, if you jot this down on any quiz or test at the top of it, it's fine. It's not cheating because it's coming from your brain, and this is what I call the roadmap. It's going to help guide us when we do all these conversions, like, because there are 3 units of measurements that we have now. We have mass, we have moles, and we have numbers of atoms. And this is going to sort of tie everything together, right? Because on one end, we have numbers, right? And then way on the other end, we have grams, or like mass, right? And this is what we do in lab. This is how atoms and molecules actually interact. Like that's how the chemical reactions are written. And in the middle, what bridges these two? Moles. Okay? So, to go back and forth between these 3 units of measurements, we're going to need, here's 1 conversion, here's 2 conversion. And it works like this. The numbers are 6.02 times 10 to the 23rd of anything is equal to 1 mole of anything, right? That's when you're dealing with numbers. Now, when you're dealing with atoms and molecules, 1 mole of any substance is equal to its gram formula mass. Its gram formula mass, or its atomic mass, or its formula mass, whatever mass you want to call it. That mass in grams is equal to 1 mole, and this is how we're going to get from one thing to the other. So, for example, if we want to know how much does, I don't know, 1.3 times 10 to the 48 atoms of lead weigh, we're going to go from numbers. Well, we can't get straight to mass. We're going to have to go from numbers to moles and then to mass. You guys picking up what I'm putting down? Same thing with mass and numbers. Like if the question is, how many atoms are in 2 grams of, I don't know, silver? Well, you can't go straight from mass to numbers. You just can't do it. You got to go from mass to moles and then to numbers. And that's how we know how many numbers of atoms and molecules we have in the sample. Got it? Excellent. Write that down. Memorize it. I need you to be able to like spit that out by memory. Okay? It will definitely help you. All right, so let's check this out. What is the mass of 2 moles of sodium? Okay, so we're starting at moles, and we are going to mass. All right, so moles to mass, that's here, right? So I'm going to need the gram formula mass for this. Okay, of sodium sulfate. Gosh, this is a whole thing, isn't it? So sodium is Na. Sulfates, I'm not really sure. Can't remember the chemical formula for sulfates. SO4. 2 minus. Sodium is always a +1, so it's going to be Na2SO4. Excellent. So to convert from moles to mass, I know that 1 mole is equal to the gram formula mass. So guess what I have to calculate here? You betcha. All right, so there's my gram formula mass. So I'm going to write down what I'm starting with. 2 moles. Oh wait, let me get this out of the way. 2 moles of Na2 SO4, and as always, that's going to go in the upper left-hand corner of my lines of pain. And if I have moles in the upper left, I'm going to want moles in the lower right. And so if it's 142 grams per 1 mole, I'm going to put 1 mole down here. And if I want grams, it's going to be 142.1 grams, because that's 142.1 grams per 1 mole. I'm going to double check. Yes, my moles cancel out. That will leave me with 284.2 grams Na2. 284.2 grams of Na2SO4. Next. All right, how many moles are in 145 grams of sodium? All right, so let's get our roadmap here. Remember, it's numbers, moles, mass. And it looks like here how many I need to get here. And so I'm going from mass to moles, right? Okay, and it's gonna put that back there. And it's going to be sodium chloride. We know that that's NaCl, right? And remember, it's up here. Let's do 1 mole is equal to the gram formula mass. Guess what we have to calculate again? Okay, it's actually starting to get a little bit easy for me here. So once again, I'm going to write down what I started with, 145 grams of NaCl, and that goes in the, again, what I start with, it goes in the upper left-hand corner. And if I've got grams in the upper left, I want grams in the bottom right. Okay, so let's go over here to my quality. It's 58.5 grams per mole. So I definitely want grams, and according to this, it's going to be 58.5. And then in the numerator, it's going to be 1 mole. Double check our units. Grams, grams. It looks like everything. Boop, look at that. Just like that, it's magic. 2.48 moles NaCl. It's as if this method works every single time. I'm telling you. It's. Oh, hey, we're done. Oh, look at that. We're all done. Let's go back here and double check here. We went from mass to moles, right? We went from moles to mass. Man, we can do it all, and right? Because we have this, our conversion roadmap. This is how we're gonna like find our way through all these things. Because if we have our roadmap written out, we can be like, okay, if I'm starting, wait, let me get a thing. Okay, if I'm at grams and I'm going to moles, okay, look, there's my equality that I have to have, right? But if I'm like, okay, if I have mass and they're asking me for numbers, I got to go all the way over here. It helps us see that we got to do this conversion, and that's our equality. And then we have to do this conversion, and that's our equality for that one. You got it? So the worksheets that are like the practice problems that are associated with this are working with moles and more moles. Write down the roadmap. It'll make your life so much easier. I'll see you guys soon. Have an awesome, awesome day.